Okay, let's look at the ionic product for water. Now, it's a bit of a strange equation. Two water molecules colliding to produce an oxonium ion and a hydroxide ion. Okay, but you saw this at IGCSE that occasionally water molecules do dissociate. So you have got some concentration of, you called it back then H plus, and some concentration of OH minus in water. Not very many though. If we wrote a Kc for this, it would look like that. You've got water squared in the denominator, but as we've seen many times, the amount of water is enormous, and therefore this number here is going to be enormous and unchangeable really on the scale of things. So this will be constant. So we're going to take that out and we're left with this. It's called the ionic product for water, and it's given the symbol Kw, and it's simply the concentration of the oxonium ions in moles per decimeter cubed times the concentration of hydroxide ions in moles per decimeter cubed. So 25 degrees C, 298 K, this has a figure that you need to remember. 1 times 10 to the minus 14. Okay, and you could, if you do minus log to the base 10 of that, you get pKw is 14. Now this isn't just something that's academic, it's going to be quite useful for us. It's a final comment there. Obviously this is a very, very small ionization. Okay. Very, very few water molecules actually break up. So we know that water is neutral, so the concentration of the hydrogen ions and the hydroxide ions must be the same. Okay. If that's the case, then if their product is 1 times 10 to the minus 14, then each of them must have a concentration of 1 times 10 to the minus 7. Okay, so what's the pH? Well, you could work this out. You can stop me if you want. And obviously we do the pH is minus log to the base 10 of the hydrogen ion concentration. In this case, plug the numbers in, and what a surprise, the pH is 7. Okay. All seems to make sense, doesn't it? All fits together. Now, we're going to use this to calculate the pH for strong bases. So we assume total ionization. If we take sodium hydroxide, then it completely dissociates when we dissolve it in water to give the ions that are present. That makes sense. The concentration of hydroxide ions in a 0.1 molar solution of sodium hydroxide is going to be, it's going to be 0.1, isn't it? It's a 1-to-1 mole ratio. Great. Now this is where our ionic product for water comes in. If we multiply those two terms together, we get 1 times 10 to the minus 14. That is a constant. So if we know that the concentration of hydroxide ions, we can plug this in, is 0.1, we can do the calculation to find the concentration of hydrogen ions. Okay, a little bit of maths. And if we know the concentration of hydrogen ions, then plug the numbers into the pH expression, and we get pH equals 13. Okay, so the pH of a 0.1 molar solution of sodium hydroxide is 13. It's quite interesting because the pH of a 0.1 molar solution of hydrochloric acid is 1. Okay, and they're like a mirror image of each other around a pH of 7. So the pH of 1 molar hydrochloric acid is 0, work it out, and the pH of 1 molar sodium hydroxide must be 14. Again, you can work it out. You will have thought about this now, and you will have realized that negative pHs and pHs above 14 are actually possible with strong acids and alkalis. Right, read the pages and answer those questions. One last comment here. In the Edexcel syllabus, we don't really talk about Kb and pKb, which is the same as Ka and pKa for the acid world, but applied to the bases world, the alkali world. And it's completely the same maths, but we don't need to use it. We can get away with, as you've just seen, using Ka and using Kw. But it's not difficult. In 5 minutes, you could actually familiarize yourself with Kb and pKb. Okay, have a little go at that.